Okay, so let's get started. So did I mess up something? So welcome everybody to this kickoff meeting.
As you prefer.
Okay. Big seminars. And, so I want to just thank our sponsors, which I call so the Professor Mathématique Adamar, CNRS, and the Institut Henri Poincaré. So there is a website which is not written here, but it exists. And again, if you are interested, there is also a mailing list. So if you want to know about these events, so we have many, like 3 or 4 events in the course of the year, and then there are many seminars online usually, and some of them will be at the peak of this year. I have lapsus. I apologize. Sorry, I just don't remember. Well, the IHS. Okay, so we will also have some further events in person. But for today, we're going to start with Antoine Tilloy from ENS, Inria, and École des Mines, who is telling us about a variational approach to lower dimensional quantity theory. And well, please go.
Thank you. I'm very flattered and honored to have been invited here to start this session. So it's going to be a very simple talk. Maybe it's too simple, so for this audience. But this way, in the upcoming hosted seminars can up the level. Okay, so. Okay, so I want to tell you about variational methods for low-dimensional QFT. By the type of quantum field theory I have in mind, as a non-sophisticated person, are theories with an action of that type. So, something in 2D. And I have in mind phi4, although it's not necessarily limited exactly to this type of theory. So I have in mind some model with an action like that, and that you compute a correlation function by a path integral, for example. Yeah. So this is like if you really see it as a statistical field, but you can also see it in the operator way, which is the one I will like today for a variational method. Where you see it now as an integral just over R. And I put hat to really insist that I have operators. And with the canonical combination relation. So now I'm really seeing it as a theory of harmonic oscillators. Okay, why do I care about these theories? It turns out they have a very nice sweet spot in 2 dimensions of being still fully non-trivial to solve, and yet we know how to define them rigorously since the 60s. Okay, so they are a sweet spot of being totally well understood mathematically, while not being so easy actually to solve directly in the continuum. So they are a nice starting point before you want to do anything fancy. And they have no integrability. So you cannot, there is no way to attack these types of methods with this type of theories with exact method. Okay, why is it actually simple? Because what I wrote, the 2 expressions I wrote are actually divergent. So this is not a well-defined self-adjoint operator on a Hilbert space. This doesn't define this doesn't give a well-defined probability measure. But the divergence is simple and fairly intuitive. Basically, because the field fluctuates a lot, like at equal points, fluctuations are infinite. The free part has logarithmic correlation functions at short distance. Lambda phi4, the lambda phi4 term behaves more or less like an infinite mass term. and that you have to cut off. You have to first smear and then subtract to get finite answers. And so basically you do that in the functional integral representation by writing the m there as the m renorm minus lambda log lambda. They are actually factors, okay, that I'm not writing here. But just to say, this is fairly intuitive, the divergence they are. And in the early days of constructive field theory, they realized that it's even simpler than that, in the sense that if you write it the operator way, okay, I should say maybe this corresponds to subtracting the tadpole. Okay, so this divergence comes from the imperturbative expansion to the tadpole correction to the propagator. Okay, good. This tadpole correction to the propagator at the first order in lambda diverges logarithmically. And the operator way, or what people would call in condensed matter, is just a Bogoliubov transform or a mode transform. Where you write the field operator in a mode basis. I guess there is 1/2 pi for the standard convention. And where these are commuting, are canonically commuting. Okay, so this is really, in a way, I think the convention is to take them commuting to 2 pi delta. And if you do this, this is textbook QFT, I know, but it's sometimes important to remember what this does for you. So if this part, you call that H0, then you have that H0, nothing changed, it's still divergent. Okay, so the free part of the Hamiltonian is still very divergent, but it's a very tiny divergence. And if you normal order it, now this guy so normal order it in the A basis, this guy is totally okay. He's a fine operator. That's trivial, that part. What is less trivial, and that what was proved in the 60s by Glim, Nelson, there are various independent proofs, but H lambda is also a fine operator. Okay, this is less trivial. And so in particular, in finite volume, the energy of the ground states, okay, the energy of the ground state or the vacuum state of this guy is exactly 0. The energy of the vacuum state, the ground state, like the interacting vacuum, if you like, of this guy is not 0, it's slightly negative. But the slight negativity is finite. It's not minus infinity, minus something divergent. Okay, so this is in a way the simplest example. And this guy, the theory defined from this Hamiltonian is a Whiteman QFT. I mean, so basically, this is as good as it gets. Okay, like there is no worry whatsoever. We are working with a totally fine object where it makes sense to make numerics without any extra cutoff, because the object is perfectly well defined. Okay, so this is there aren't that many models, but in 2D, whatever potential, it's still true. For any potential that is operating phi, E alpha phi, and E alpha phi for alpha small enough. And I will not say more about that. Okay. That's okay. So I apologize if this is insulting so far. Just wanted to, so like, at least if you can see quantum field theory in 1+1 dimension, just as a composite matter problem with a Hamiltonian space of states, Being naive is good in 1+1 dimension because that still works and that's easier. Okay, what's the physics of these types of model? Well, in PV, so at short distance, it's like the C=1 free boson. So at short distance, you don't see the interaction at all. And in the IR, well, it's massive. So you have a gap with m that is a certain function of lambda on m. And if you fix lambda over m squared equal 2.77, and the exact value is not known, it has a second order phase transition. That's in the Ising universal thickness. Okay, so that's a. But even so, and then in that case, the IR is Ising. But the full theory is still not Ising. Okay? Like there's a wide difference of scale. It's still C=1 at short distance, and you get C=1/2 at long distance. How do you, okay, so this is a well-defined theory, but how do you solve it now? Let's say you want to solve it. And in particular, you see that this is a large value, okay? So to see a phase transition, you need to get to fairly high, large value. And so for solving traditionally, historically, there was basically two methods, okay, like Monte Carlo, but then you have to discretize, which I have nothing against discretization. I think if it's well done and it's well controlled, that's all right. But that's a bit of a pity. This theory is completely well defined without any cutoff in the continuum limit. And then there is perturbation theory, which doesn't require a cutoff. So in a way, it's nicer in this respect. It's directly well defined in when the UV cutoff is sent to infinity, like the energy is sent to infinity, and the infrared cutoff is also sent to infinity. But of course, you're going to be restricted to, say, lambda smaller than 0.3 or something like that. And if you Borel resum, you can do better, but I will assume we are not so sophisticated right now. Okay? So now come the variational methods. Are there questions about this theory? I should say perhaps something that might be surprising is that if you have in mind like this, the potential reversing and the effective potential having double, well, it may seem surprising that the theory is symmetric, and symmetry breaks for when the coupling gets larger, which seems to be like the opposite way of what should be going on. But this is because your normal order, you subtract a tadpole. So you're basically, as you increase lambda here, you turn on an infinitely negative mass and you make it larger and larger. So in fact, you reverse the potential even more. Okay, so for lambda large, the effective potential is really something like this. Okay. So the idea of the variational method, which is probably one of the promising non-perturbative methods to solve this, is to really take seriously the fact that it's a Hamiltonian theory in a Hilbert space, write states and try to find the ground state. So you can write the Hilbert space. So what I will explain first is this Hamiltonian truncation. Here. So the Hilbert space of this is just the Fock space of L2 of R. So you define this mode operate the vacuum state, which is such that for all P, okay, yeah, use K so far, AK of 0 equals. This is the bare vacuum, if you like. And then you can define any state by summing all the possible occupation numbers in this Fock space. That's the most general state you can write in this Hilbert space, and that's like if you like the n particle wave function. If we were in first quantization, okay, we would interpret this as an n particle wave function. And so in particular, even the interacting ground state, like the true vacuum state of the theory, I can in principle write this way. And so I can try, the objective of the variational method is to make a conjecture for this phi n of x and optimize them and try to really explicitly write this ground state of the theory in the Hilbert space that it has. Okay, so this Hilbert space is also legitimate. In fact, if I really put it on Rn, it's a bit of a problem, so I should put it in a box, but at least there is no UV difficulty with it. So what I can do is, so what I do, I put it in a finite box, in which case if you like, the Hilbert space become some Hilbert space in a box. And my k's that are continuous become k high, like a discrete set of modes. And in particular, as a result, if I put my system in a box, the Hamiltonian matrix here. Sorry, this is not my notation. Is also K prime M. This object is an infinite matrix, but sort of with discrete entries. And that what I can do is also now consider only states that are below a certain threshold that I call HC. Probably I should truncate with S0, but one of the choices to do this. And with this, I get an even smaller Hilbert space, which is cut off both in maximum occupation number, if you like, or maximum energy, and in a box. And if I do these two, putting in a box, putting a maximum energy, the Hilbert space is finite. Okay, this guy here is finite dimensional. Okay, and so now the Hamiltonian in this system is just a finite dimensional Hamiltonian, and you can diagonalize it using Long-Shos or whatever algorithm on the market to diagonalize a finite matrix. Like we have gone from quantum field theory to the quantum mechanics we learn in first year of quantum mechanics. Okay, so the Hamiltonian you can write like this: that restricted at site L and maximum cutoff energy EC is just a matrix. So can be diagonalized. And this is the important to have in mind, because this is the simplest, the most trivial instantiation of the variational method in quantum field theory. And I mean, it's already very good that we can do that, okay? That this doesn't come with any divergence, at least for this model. But it has one drawback. Yep. Yep, sure.
Do you have a problem with Planck theorem?
No. All of that I think is in higher dimension. So here, the Fock space, the true ground state is a state that belongs to the Fock space. So no, there is going to be an infinite volume problem. Okay, so and as we will see, this method doesn't scale well when I take the infinite volume limit. So here I'm really, when I'm saying that was improper, what I should say, the guy that is well defined as a Hilbert space is this guy. But all correlation, okay, like the quantum field theory is well defined for all the real line. And then because I can take easily limits of correlation functions. But if I want to define a Hilbert space, at least simply, not a la Whiteman, if I want to define it from a Fock space, I should probably always take a cutoff in size.
So when you're saying H lambda is about to find operator before, this was on something different than the Fock space that you use IR regularization?
Okay, I mean, it's still, for me, I was a bit sloppy. Like it's still a self-adjoint operator only on finite. In particular, the ground state energy is not going to be lower bounded if you have no infrared cutoff. So it's always assumed when you say energy is lower bounded that you mean in the with a box, because since it's extensive, these are extensive quantities, the spectrum is going to bottom down. But this is sort of a trivial bottoming down compared to the UV bottoming down of the spectrum that is considered really problematic. So indeed, maybe for all the statements about rigor in the Hilbert space picture right now, assume that there is a box. But so for those who are familiar with condensed matter, I mean, this suffers from the same problem as exact diagonalization. You can solve a spin problem on the lattice, but the cost increases exponentially with the length of the number of sites. And the scaling here is exactly the same. I should say first, the error of the method is in 1 over EC squared. Okay, I'm being very sloppy. I'm not saying for wide observables, but say for local observables, it's in 1 over EC squared. And people have done improvements using RG to bring this to higher powers. I think the best is cube. Maybe we can do fourth now, I'm not sure. But this is not so important, is that the cost, so which is really the number of states of state Hilbert space, is proportional to exponential LEC. There is a constant, okay, but it's exponential both in the cutoff energy and in the length scale in the size of the system. And this is fairly intuitive. It's the same exponential increase of the many-body problem on the lattice. Intuitively, you see that if we write the state in the Hilbert space like this, and imagine the particle density is finite in the ground state, if I make the systems twice larger, I will need twice more creation operator here to get the same quality of approximation. And necessarily, this means that I have far more operators, because if I have now double the number of creation, the number of wave functions I can write here is growing exponentially, okay, in this number. So I think one way to summarize this is that, okay, Hamiltonian truncation of HT admirably solves the UV problem by working in the appropriate Fock space, but doesn't solve the IR problem. Where you still have the many-body problem. Okay, so it still can be very good, because sometimes we're totally fine by having the system in a small box, and we don't care about insane precision, so we don't need EC to be super large. But interestingly, and this will be my next step, on the lattice, so for lattice problem, I think it's something that is well known in some communities, but not in others. In condensed matter on the lattice, in 1D, the problem was essentially solved in the 90s. And now numerical results in every paper are quoted as exact. Okay, so that's a bit surprising at first, but when the MRG was introduced in 1991, no one knew how to solve the spin chain with 1,000 spins. And all the approximation methods were good, I don't know, to 30% accuracy. Okay, they were garbage, like they were rough estimates. The next day, all these models were solved, basically. Okay, so now some of these results are quoted with 16 digits. So they are not solved, okay, like it's still a numerical method, but practically, the many-body problem on the lattice in 1D was solved. So the infrared problem in the setup where you don't have a UV problem was solved. I'm a bit exaggerating, okay? I will be happy to make this to be more cautious about this statement later if you have questions, but I think it's so underestimated that I don't feel so bad exaggerating a little bit. Okay, and the core idea, and really the core idea, there are many ideas. There's a lot of talking about entanglement, why DMRG works, but I think the real idea is to go from a subspace of the Hilbert space, you go to a manifold. or submanifold. So you break linearity of your parametrization. Okay. So instead of if you like, you have the total Hilbert space is the board or the ambient space. Hamiltonian truncation is really trying to carve a linear subspace inside it and have states live in it. And what the modern methods on the lattice do is, I don't know, they are carving some sort of curved manifold that has much better properties as the system size is increased. Okay, so the idea is that the idea of matrix product states on the lattice was really to have this kind of manifold. So you belong to a manifold that is included in the Hilbert space. Well, once you have a manifold, you cannot really solve an eigenvalue problem in a manifold. Like it doesn't really make sense. It's no longer a linear problem, but it's still a variational problem. Oh, terrible notation. Let's call it a nu. Okay, these are coefficients. These are, if you like, the coordinates in my manifold. Okay, my manifold has certain coordinates that tell me how I move in various directions, and that's how I parameterize my state. So it's still a variational problem. And you can find the ground state. So, okay, I'm very condensed matter influence. So I say ground state, you really have to think interacting vacuum. I over-insist so that we don't confuse with the bare vacuum, like the fog vacuum. It's going to be approximately, if you chose your manifold right, psi nu h, sorry, I forgot. GS is going to be argmin over this manifold. Okay. It's not going to be exactly for all the psi nu. Of course, it's not going to be exact. It's going to be an approximation. But if I guess my manifold right, this is also a legitimate method to find the ground state. Now I'm going to assume I can always do this optimization, because one thing is to define a manifold, another would be to carry this optimization, and that would be possibly non-trivial. And it turns out that when I say the many-body problem is solved on the lattice in 1D, this is true up to this, in the sense that the optimization always works, but it's not possible to prove that it will always work. Okay, and so the right manifold on the lattice is MPS. You want to take M as the matrix product states. And I won't say much about matrix product states. I'm trying this to not say anything about matrix product states. I will just say the state I will define in quantum field theory is inspired from it. And the fact that I know that it was solved on the lattice is what gives me a good intuition it will work. But you could still work directly with this state, and we can verify directly that it has good properties. Okay. And one thing you need to know about the solution on the lattice is that it works in real space. Real space is a space in which entanglement is moderate, and so in which these compression methods that people have found on the lattice works. There is no compression possible in momentum space, at least not naively, because momentum space has what's called volume law entanglement. So states are very complicated in momentum space in terms of entanglement structure, in terms of information. So what we have to do is to do this ugly step and work, instead of a Hilbert space in momentum space, work back in position space by defining these absolutely ugly operators that every time I make this presentation, people find it insulting. But what I can guarantee is that we've thought a lot about it. And it seems this is really the right object that you want. And okay, empirically, it works. And we have no nicer looking proposal. So I defined this Fourier transform of this annihilation operator, same way for the creation operator. Why I say they are ugly, because there is not the over root 2 omega p. So this thing is not at all, doesn't have any good covariance properties, okay? Once you work with the variational method, you have abandoned this, okay? All this business is gone. You don't care about being covariant or anything. if I could find the true ground, if I could have a variational state that had the right invariance properties, it would already be the ground state. So I would be done, okay? Because it would be the only Poincaré invariant state. So I'm screwed anyway. So I can break everything and I will recover through variational optimization a state that has large properties. So I will create my states from these guys, which don't have nice transformation properties. They are really defined in a certain frame. But I won't say we don't care. Okay, it's not so bad. In the variational method, this doesn't come with any problem. And why is this much better than putting the over root 2 omega p for what we want? Is that what you have is that you preserve the commutation relation. So at least intuitively, this factorizes the total Hilbert space in a product of local factors. Okay, this is kind of an artificial. I can really interpret as the Hilbert space is made of physically localized oscillators everywhere in space. Okay. Do I say here why it's going to be bad? Yeah. This is nice because it gives sort of a local transfer product structure. It's as if you like, it's as if I had really a lattice in X where I have an oscillator on each side. Crucially, these oscillators are very different from the phi oscillators. You know, we say, oh, a quantum field theory is just a theory of interacting harmonic oscillators if you discretize it. We are not talking of this. We are talking of the oscillators associated to phi, and I erased it, phi and its conjugate pi. These guys are non-local in the field. I think that's important to have in mind. So phi of x is unfortunately not a local object with respect to this. It's j of x minus y. Sorry, y. It's a convolution, and j. So now I gain a locality of the Hilbert space structure. I lose it in the Hamiltonian. But as we'll see, what's still good is that j of x decays exponentially when x goes to plus infinity. So the phi is not local in A and A DAG, but it is local-ish. Okay, like there are no long-range correlations that are going to build up. And now I drop you just by saying that this is really inspired from MPS. What are these relativistic continuous matrix product states? Which are a state parameterized by two matrices. Okay, I will explain what every term means here. It's a trace over the space of matrix of a path-ordered exponential. Here I will put it in a box and just a second later say that the box is not needed, but if I want to be rigorous, the state itself is not defined in a box. In the thermodynamic limit, only correlation functions of the state are. Okay, so now I can tell you what each object is. So these are two matrices that are now parameterizing my state. So there are two d times d matrices. And they contain 2 times d squared complex coefficients that are my coordinates on the manifold. They are the knobs I will tune and optimize to find the ground state. This is the trace over d by d matrices. This is the trace over d by d matrices. This is path ordering. These are the matrices, and these are Fock space operators. Okay, the identity, and this is Fock also. This is just to make sure that we understand what's going on, is that the big thing inside is an operator acting on a tensor product of Fock space and d by d matrices. And then I take the trace over d by d matrices. So now this whole thing is an operator on Fock space. So at least I'm not completely crazy in that this is an operator that lives in the right Hilbert space. Okay? So that much is done. Now, the path ordering is this presentation is the one that's really useful to make calculations to understand why it works. In particular, you notice that I can increase the system size here at no cost. I mean, this is just a parameter. And the fact that there is an exponential in it is kind of what suggests the extensive nature of the parametrization. That I'm sort of locally parametrizing it, and as a result, I don't get this explosion of the number of parameters. But to be a bit more explicit, I can give what is the n particle wave function. So I can Taylor expand this path order exponential. I Taylor expand it, and it's going to give me, the creation operation are going to pop, and this is going to give me a state written in the original Hilbert space. Actually, here you didn't protest, but these were supposed to be k, okay? Now, what I'm going to give is, now they are in space. So I just write it under here because this is, I want to say, this is the n particle wave function, but in real space.
Q and R on the same level varying.
They are the parameters, yeah. They are my free parameters. Q and R are the free parameter. Are free to choose, like you're going to tune them. And now you want to see, I think, so this is still, this is a trace. Yeah. So several comments is that all these phi are non-zero. Okay, they have a sort of hidden internal structure, but the states we construct this way is not sparse. It is really populating the whole Hilbert space. Infinitely energetic states in particular. So there is no obvious cutoff in the Hilbert space. We're going to put weight everywhere, but they are highly structured. And in particular, they are non-trivial because Q and R don't commute. If Q and R commuted, this state would just be a sum of coherent states, of field coherent states. Yeah, so really, I insist.
You think this is dense subset or?
Okay, to be totally honest, this is not fully proved that this is dense. What is proved, and that is actually completely trivial to prove, is that you have a generic state. Then you can approximate it by having Q and R x dependent. Now, if you have a translation invariant state, you should be able to approximate it with Q and R also translation invariant, so independent on x. And this is not proved as far as I know. I should say it is expected that the standard argument for MPS follows through and that this is done since Fock space, but this is not at the level of rigor that one would desire. In any case, okay, density, but you're right to ask the question. Density is a very important question. Is it dense? And I think, okay, it's reasonable to expect this is dense, that if Q and R increases, you get arbitrarily generic correlation functions, n particle wave function, and so you can get any state in the Fock space. What matters is it efficient? Because since the Hilbert space is infinite dimensional, we could be dense and be absolute garbage in the sense that we would require, I don't know, it could be that we would need LD doubly exponential in the error or something like that. That would be a disaster. Okay, so this state doesn't depend on the system size, and it has other qualities that I have to give. So. Okay, so it's clearly a manifold also. So if I sum two of these states, it's not a state of this form. Okay, it's going to break. It's not stable under summation. But it has good properties. So as I said, it's extensive, and that's something we wanted that we didn't have in Hamiltonian truncation, unfortunately. Yeah, it's highly plausibly dense. Okay, before I was saying it was proved that it was dense, and I realized that it's not totally true. So I plausibly dense in the translation invariant case. And it is computable, and that is the most important thing, and something I'm unfortunately not showing here because it's technical. But if you give me whatever operator that is local, say a polynomial in, whatever, polynomial in phi, normal ordered, this is computable. Sort of, when I say exactly, people are annoyed, so numerically exactly. What I mean by that is that even when you compute the exponential function on your computer, it's a numerical computation. Okay, it's always approximated. In the same sense, we can get 12 digits for these quantities, so they are exact for all practical purposes, even though technically we have no analytic formula for them. And the cost is d cubed. That's the cost of matrix multiplication. We have matrices, we manipulate them, and at cost d cubed, we can compute observables in this state. Fortunately, we don't have to decompress the representation. We could imagine that we would have to go to this representation, so decompress this and compute correlation functions by summing all the wave functions that appear. Turns out the computations are doable in the compressed representation, so only by simple algebraic manipulations on Q and R. The cost is d cubed. And even more importantly, now if you evaluate something of that type, okay, I should have. Now it's translation invariant, so I will evaluate the Hamiltonian density and not the Hamiltonian. Okay, because this the energy of the ground state, as usual, is going to be infinitely negative. But if I take the energy density, this is equal to, if you like, a certain function of Q and R that you can compute again at cost d cubed, but that is not infinite. Okay, it is a finite thing. So we're not sort of. It could be that we introduced new divergences because we chose our ansatz carelessly, but that's not the case. The ansatz is well adapted to the quirkiness of this quantum theories. There is no, you have to be careful that I'm held on the line here. Okay, I will. Okay, I'll let you digest the profound things I just said. Okay, so these are, if you have ever worked with numerics, these are all very good news. Okay, like when you don't have this, you are fairly unhappy. And so since we can compute this, another question is, can you compute this? The gradient with respect to Q and R of this function here. And it turns out this is also now you forgive me for the exact at cost d cubed. So you can compute the full gradient also at cost d cubed. And so you can optimize it with gradient descent. Okay, and in this, just optimize it with gradient descent lies an infinite literature of how to actually do it, because turns out gradient descent doesn't work. So you have to use Riemannian gradient descent. Or it's second order improvements. But sort of, this was understood before on the lattice, how you do this optimization. You should be slightly less naive than what I say here, but this is optimizable. And so at the end of the day, you get that the ground state is approximately a certain Q tilde and R tilde that you found by minimizing the energy density.
So is the problem convex somehow?
No. No. But what we have, the intuition we have is that if you do the proper Riemannian gradient descent, the physical intuition is that it's like doing imaginary time evolution for a little bit, which cools the system down, and then reprojecting on the manifold. So every time you evolve a bit in imaginary time, you leave your manifold, but then you force it back. And imagine if the manifold is good enough, the effect of the projection is going to be smaller. And so effectively, you're cooling it down. And then it could be that a system that you cool down stays trapped in local minima, but that's not a common thing you expect in QFT. Okay, optimization of non-convex problem, you are never going to be able to prove that it's efficient because we can hide hard combinatorial optimization problem inside, but what we can hope is that for all practical instances people have tried, this converges. But it doesn't come with guarantees like, say, in semi-definite programming like you have in the Bootstrap, where you have really guarantees that the optimization program converge in 20 iterations. So here, I don't know, I'm like, Sophie and Karan were here, and depending on the problem, it takes from 100 to a few thousand iterations. It depends on the, it's not crazy. It's not like it's not like billions of iterations. It's like, if the matrices are small enough, it's a few hundred max. And what we see is that the error on local observables, again, this is not a fully scientific, but seems to be decay suprapolynomially. So the method has a polynomial cost as an error that decays suprapolynomially. So in principle, it's like you can approximate local observables arbitrarily well. Turns out that right now we are still in the regime where the bond dimension, the size of the matrices we take is typically 32 by 32 max. So okay, I mean, the precisions are not absolutely insane. They are still just normal. So, but the energy density, for example, you can get 5 or 6 digits probably. And the belief is that from the scaling we see, if we just threw more compute at it, it would just get better, and we would, but fast better, like much faster, better than say Monte Carlo. So I have 10 minutes, but I guess I should take off our questions. Yes. Okay, then there was some open problem that I can mention later. I think it's better if I okay. No, you don't have to. Okay, so thank you for your attention.
Okay, so thank you very much, Antoine. I have, of course, a question.
No. You're not allowed.
Question, please.
Yeah. I have one concern. If it's a Euclidean setup, the probability matter is not divergent.
Sorry, can you say again?
The lambda phi 4 you mentioned, if you just do it in Euclidean, fit it as a probability measure, is it well defined or?
Yeah. So it's again, the naive path integral I wrote at the beginning is ill-defined. But if you cancel the tadpole, or equivalently, if you normal order in the normal mode basis of the free part, both these operations are actually mathematically equivalent and cancel all the divergences. If we move to 2 + 1 dimension, and that was one of the concerns, I was very honest, so I phrased it as variational method in low dimensional QFT, because if you go to 2 + 1 dimensions, first the tensor networks become much worse, and that's the first problem. But even on the QFT side, you have the problem that there are subleading divergences to the tadpole. In phi 4, the sunset diagram diverges. The constructive field theorists have understood this a bit later, actually, not in the 60s, in the second wave of constructive field theory. And so this theory is still well defined, but they are sort of much harder to get well defined. And in particular, the Fock space description is no longer valid. So you still have a Hilbert space, but implicitly from Whiteman's construction. And this is a completely unusable Hilbert space because it's the Whiteman construction requires solving the theory exactly to get the Hilbert space. That's the advantage of these low dimensions, is that we have the naive Hilbert space, we can still write stuff in it. I think that's the important thing that allows even non-integrable models to be solved.
Other questions?
this ansatz you took for the state, will it work for any potential in the Hamiltonian, or is it somehow well suited for these?
No, so that's a good question. So right now, okay, all the potentials of all the polynomials are going to behave the same. Like there is no difference whatsoever. And all the exponentials, either complex, either imaginary exponential or real exponentials, are going to work up to the threshold. So there is this threshold. So if you have E alpha phi, there are two thresholds. It becomes non-renormalizable at all for alpha larger. If alpha is larger than square root 8 pi, in my convention, you're totally dead. The theory is not even well defined. But if alpha is larger than 4 pi, there is a subleading divergence already, the first subleading divergence. And this is dead already for us. So in this region between 4 pi and 8 pi, the theory still exists, but we can't solve it. That's the band that's problematic right now.
Can you do like both exponential and exponential minus I alpha?
Oh yeah, no, that's what I meant. Yeah, so this is yeah, you're gonna define a cosine. Yeah, okay, this is not even Hermitian. Say cos alpha phi.
Can you compare it to the result from sine order?
Yeah, you can. I did it. Yeah. It works. Yeah. Okay, and this is something what I could mention is that the integrability result for Singe-Gordon exists but are questioned because maybe you've heard there is all a fuss around it. So we don't know. And what I could check numerically is that for small enough values of alpha, they seem okay. And after a while, we diverge. But what we see is that no method converges well. So right now, it's not so clear exactly for the Singe-Gordon theory where is the threshold, where it stops, where it starts breaking down. Okay, but there are very people thought they had solved Singe-Gordon, that it was totally solved until arbitrary values of alpha, basically. And now we realize when we do numerics first, it doesn't match the integrability. So it's possible that there is the analytic continuation for Singe-Gordon from sine-Gordon breaks down at a certain point, like maybe the solution branch or whatever. And that is not something you're going to see very easily from analytic continuation. In principle, these numerics would work, but precisely at the interesting point, what we see is all of a sudden our convergence becomes absolutely garbage. Like I need to push the bond dimension a lot, and still there. So it seems something happens to the Hilbert space, or like maybe the Hilbert space is no longer right at this point. But this is poorly understood. At least if you say if alpha is smaller than square root 4 pi, it's totally okay. So then we can do right now. Karan is working on O2, having several fields. We're trying to put fermions into it. I mean, there are various extensions, but at least for bosons with these types of potential, I mean, there is a working code that is giving you ask it for an expectation value, it gives you the value. This I would say this is stabilized, and then the rest is in progress.
Okay, so thank you very much. And any other question before we conclude and go for the break?
Yeah, can I ask a question?
Antoine, again.
Do you hear me?
Yeah, I could not. Yeah, no one would say. I will just leave it the way it is.